We're going to cover over some topics briefly, talk about the quiz, talk about maybe your homework if you have any questions, and then maybe we'll pad it up with a little bit of review at the end. So shouldn't be too much content today. These topics will be on your final, but they won't be extensively detailed. So, okay, hit record. Last day. Yeah, let's go. All right. You guys excited for vacation? All right, but before you do, we gotta wrap up some few items. All right, we have. Let's go ahead and pull up your class. Okay, so assignments. Okay, so I think was it 6A is due today? Assignment 6A. Yeah, this one's due tonight, and then you have your last assignment due tomorrow night. These two homework assignments should help you prep for the exam. They're not particularly hard homework assignments to do for the risk architecture. Quiz 7, I graded them this morning. Most of you did pretty well. There is an audio check. Check your audio input or volume. Oh, can't hear anything. I think my side should be fine. I can lower the gain of my mic. Anything? You can hear me? Okay, perfect. Okay, so yeah, it might just be on your end. Uh, okay, perfect. Okay, so yeah, pass back quiz 7 to you guys. Most of you did pretty well. Just make sure that you touch up on a little bit of the MIPS instructions. We can go over that maybe later at the end. Quiz 8 I gave you should more or less be another free 10 points, so make sure you do that. We'll be able to answer everything either from yesterday's lecture or today's lecture. So the first couple of questions should be all yesterday's content. And then think, yeah, question 5 is and on is all the new topics. So only 3 questions, one for each topic we cover. So you should be able to answer all of these tonight. And I made them multiple choice slash multiple check boxes just so you get your answers pretty much immediately, so you can use that to study for your exam. So someone has one question about the MIPS output. When we want to output a value, do we do a load word A0 register, or is the name of the variable, if that makes sense? So, okay, we can go over that really quickly. So for your homework, remember your syscalls for the risk architecture, or at least MIPS, right? We have to load into A0, so we'll load immediate, or V0, sorry, either 1 or 4, depending if you want 1 for, I think 1 was integer, right? Integer, and 4 was for string. And then, so either you'll do for integer, if you want to do a value, you'll do a load word the value into A0. So whatever your variable is, and then you do your syscall, and the simulator, what it does, it ends up calculating any other extraneous things you need. So that's it. Or you can do a load address A0, and then the string, and then the syscall at the end, and that will give you your string output. So, all right. Now let's go ahead and start talking briefly about some lecture topics. Right, we have cache pipelining and virtual memory to cover, and then that should be all the information you need for this class.
For an array or list, would we load word A0 to print it? That depends on what your array has. I'm assuming if you have something like a list, right? You have, say, size word. Let's just put in 3 values. Length maybe of 3, something like that. And you wanted to print out each one of these, right? You would do a print loop. So first what we can do is we need to store the address of the list. So load address into a saved register. So in this case, we set LST as our list. Then we can load the length into another saved register. Okay. So this one is the address of list, and this one is the value of length. Okay. So if I wanted to print the first item, so imagine my list being like this, somewhere in memory, of 2, 4, 3. So here is where the address of the list starts, right? And this is the address of the list plus 4 because it's a size of word. And this is address of list plus 8. So if I wanted to access the item, I would need to give it these addresses. So in a print loop, maybe if you wanted to print each item, we can do li v0, just the convention. And these are values, so we'll just give it 1 to print an integer. And then we do la. Well, we don't need to do the la because we already know the address is in S0, so we can just do a move. Let's see, move A0, S0, right? And then do a syscall. So the first time this loop is called, S0 is the address of list, so I know that it will print out this this much, right? This value. Okay, and then I need to update, right? So I need to update it by adding to S0 4. So this is effectively whatever the address of LST is plus 4 the first time it runs, right? The second time we'll be adding 8, and then the third time, and so on and so forth. And then we subtract our counter. So our counter was stored in S1. So S1, we subtract 1. And then we can print a line feed here. So if you want to do that, maybe we can do li 0 or l a0 lf, and then maybe we defined lf here. So maybe we did lf ASCII /n, something like that. And then do a syscall. So remember that syscalls are function calls. And with function calls, only our saved registers are guaranteed to come back with values. That's why we're using S to store both our length and our list address. So that way they come back to us after the syscall, and we can make sure that the next time we use those values, they'll be updated still. Okay. So this is to print line feed, and then we have to compare it. So v not equals 0, or branch not equals 0. We take our register, so we go ahead and say the counter, which is in S1, and then we jump to the label, so print loop, and that should be how you print each item in an array. If you just wanted to do it manually, you can always do some n value LST like that, right? So store that memory space. So n being a number, so either like 4 LST is the same as your LST plus 4, right? So in x86. So I believe the load instruction is only for. So I think load and save, right, are for memory. Move is register to register, and then immediate is I, and then address is A. So just be a little bit careful with that. Well, load with a data type, I should say. Load like that. That use L. Okay. So let's I hope that was on a new layer. That was not on a new layer. One second while I fill out this layer. Okay. So let's go ahead and talk about our lecture topics. Someone asks, does this automatically add spaces between each of the values they print? No. We talked about this in the last section. What would happen if you printed without the line feed? So without this code here, this code right here, you don't get any line feeds. So you'll end up printing 2, 4, 3 next to each other. So with this code injected, your new output would be 2, 4, 3, like that. You can also choose to print blanks or spaces, right? And so instead of defining a line feed, maybe you define space. And you just do that. And that's how you could separate it, or you can maybe format it with comma and then space. So just remember that in the simulator, it will read all the characters in the string for you. You don't have to give it the string number like in x86. But that is not the design of MIPS. That is the design of the simulator. So. Do we store return value in v0 before calling JR $RA? Yes. So v0 is your return value. This is pertaining to the homework. But for function calls, v0 is the return register. Right? So this is the equivalent of your RAX in x86 when you return. So you want to have whatever value you're returning in v0 and then call your jump return. Okay. All right, let's move on to some basics with caching. So I'm sure this is not a new term for a majority of you, but we have to give an introductory to cache, which is going to be covered more extensively in 219, but more as a precursor for now. Okay, so inside the CPU, depending on what your chip is, maybe we'll just work with a 2-core chip from the early 2000s. Let's say you have a 2-core chip, and we have 2 levels of cache in this case. Sometimes you'll see 3 levels of cache, but basically the first level of cache is going to be the fastest, then the second level, and then any subsequent level after that. So here's our basic von Neumann architecture. Here's RAM. Maybe you have more RAM. Maybe you have 2 sticks of RAM. All right. So forgot to ask, do you have that MIPS PDF? Yes, the MIPS PDF is uploaded in here. So right here, MIPS PDF. So I uploaded this earlier this week. But yeah, if you want to reference it, you can go ahead and download that. Okay, so with the cache, so here's your CPU chip. Each one of these are your cores, and then these are your level 1 cache, and then your L2 cache, level 2 cache. Okay. So the further away you are from the core, obviously, the more latency you have to load the memory to your registers, right? So you can load a variable. Let's say you have a variable A in RAM, right? So what cache basically does is, first let's load in the variable once. So we use up the bus, and then we store A into level 2 cache, which then maybe gets copied to level 1 cache, and then the core here will utilize the variable A. Right. So as long as the memory and cache isn't tied up, there's no need for it to delete the contents of A. So if it's still in cache, any of these cores can basically obtain these values, these memory values, without having to ask the OS to grab it from RAM. Right. So the main takeaway for having cache is 2 things. So 1, we avoid bus contention. 2, we reduce memory latency. Sometimes we just straight up avoid memory latency, but right. And so you'll learn a little bit more about how the values in cache kind of move around in a later class, like 219 or 370. But that's not going to be important in this class. This class is just an introduction to something like this. But since we always talk about memory efficiency and the von Neumann architecture and bus contentions and stuff like that, this was a nice little rendition on top of that. So all you need to know on the test and on the quiz is that cache is designed so that we can avoid bus contention and reduce memory latency. But just be aware that the higher level the cache is, the faster the transfer of your variables are. But the space is more and more limited depending on how high of a level cache you're at. So, okay. So, hopefully not too bad. We'll talk a little bit about pipelining as well. So, pipelining. So, pipelining is a concept we introduce also for improving performance. Right? Okay. So you might have done a little bit of pipelining in real life without knowing it. But essentially, we can kind of relate pipelining to a sequence of tasks that you do in a particular order to save time. So the classic example is doing your laundry. Spell laundry. So let's say your laundry consists of 3 tasks, right? You have to wash the clothes, you have to dry the clothes, and you have to fold the clothes, right? And each one of these takes, let's just say it takes your machine 60 minutes, and it takes your dryer 60 minutes, and it takes you maybe like 30 minutes to fold. Okay. So if we break these down, right, obviously, maybe you're doing laundry for the whole family. God bless your soul if you do. But let's just say you have maybe like 4 loads of laundry to do. Let's do 3 loads, so I do less math. 3 loads of laundry to do, right? So the first time you do it, if you were to do these tasks sequentially, right? So in order to dry the laundry, you have to first wash the laundry, right? So, okay, we'll do a wash here. Okay, then we can dry the laundry, and then after it's dried, then we fold the laundry, right? So this task takes 60 minutes, this task takes 60 minutes, and then this task takes 30 minutes for a total of 2.5 hours. Okay. Okay, then let's say, okay, this is load 1, right? Okay, let's say after you've done that, then you're like, okay, well, let's start on load 2, and you wash load 2, you dry the load, and then you fold the load, right? And that takes another 2.5 hours, right? And then you do it one more time, right? So while you get the tasks done, the total amount of time you've taken is quite significant, right? So if this is 60, 60, and 30, so for 3 loads, the total time you've taken is 5, 6, 7, 7.5 hours, right? So 7.5 hours, right? But what happens if you decided to do this instead? So, well, we washed the first load. Once the first load is done, we dry the first load. But now that the washer is done here, we can immediately start washing the second load here. And then we can fold the laundry, all right? The dryer is done after this block happens, so we can dry the second load whilst simultaneously starting the third washer load, and then folding, drying at the same time, and then folding at the end. So it turns out that if you kind of split your process and pipeline it in this kind of way, right, the end result is 60, 60, this is another 60, it's another 60, and this is 30, right? So the total time you take is 4.5 hours, right? Which is almost twice as fast as the original method, right? So pipelining is a way to kind of make it more efficient, right? Breaking down your process and improving your performance like that. Okay. So when it comes to your processes also follow a very similar kind of pipelining method, right? So when you're talking about pipelining for a process, it gets broken down into a few steps. So we have the instruction fetch. So this basically grabs the next instruction in your code, right? So either your $PC or your your RIP register, right? Remember that these point to the next instruction to be executed. And the reason they do that is because it's pipelined, right? So while you're executing the current process, the pipeline already is fetching the next instruction. Instruction decode. So basically, you have to convert those ones and zeros into those, or your instructions into those ones and zeros for your machine. And we already know that in the RISC architecture, because there's less instructions, the amount of looking up and decoding those instructions is significantly faster than something, say, like the CISC architecture, which has a lot more instructions. Then we go ahead and execute the instruction. So just perform whatever the operation is after we looked it up. And then we have two steps that are kind of based on whether or not you need to do them. So memory operation. And then you have the write block. Okay. So both of these may or may not occur, right? Depending on what your instruction says. If your instruction says move a variable into a register, then you need the memory operation. And if you need it to write back, then that would also be a writing operation. So depends if your instruction uses those or not, but in general, this is kind of the dissection of it. Okay, so with those, let's go ahead and maybe do an example with 5 instructions, right? 5 instructions. So it might look something like this. So first, 2, 3, 4. So first you grab the instruction, then you decode it, then we execute. I'll use M for memory since I don't know if I'll fit that, and then write block. Okay. So once the instruction's been fetched and we start the decode, we can go ahead and start the next instruction fetch. Decode, execute, memory, and write block. And this happens 3 more times for the next 3 instructions, right? IF, ID. Of course, sometimes it might not happen. So let's say in this case, we have IF, ID, and then we execute, but there's no memory instruction. And no writing instructions. So this one is done. Okay. But we still have to wait for the IF to finish here. So, and then maybe we just have a writing instruction. So that could be what a pipeline for a program with 5 instructions might look like. Okay. Any questions on caching or pipelining? And then let's go ahead and touch up on the last topic we need to introduce. And then you'll see all of these come back to haunt you in 219 or 370 or some other classes. But at least you'll be exposed to the concept. So virtual memory. So next and last topic. So while this has a lot of overhead, so I guess if you wanted to talk about the negatives of having virtual memory, we induce a lot of overhead, but we gain access to a lot more memory usage, right? So the ability to run larger programs that would not otherwise fit. Okay.
So, for example, let's say maybe you downloaded a game on Steam that was like 16 gigs of storage space, right? But you only have 4 gigabytes of memory in your Raspberry Pi, and you're like, well, how am I supposed to load this game and play it uh, on my device? But it's actually doable because of this concept called virtual memory that all the programs utilize. So, if you were to look at your debugger, right? Let's say this is your addresses in your debugger, right? So if you were to open 2 different instances of your debugger, you would notice that the address in your debugger are basically virtual or fake, right? So essentially, that is something like let's say we had a pointer here, right? If you were to dereference the point, or not dereference point, but if you were to extract the address of this pointer in 2 different instances of your debugger, you'll get 2 different addresses. And you might be thinking, well, how can that be? The program fits into, let's say this is your stick of RAM. Your program may sit somewhere here, right? So this is maybe hello world. Hello dot hello dot right? So maybe this is where your program file sits, and you're like, well, this part of my program should not change in address, and it doesn't change necessarily in the main memory of RAM, but because of this virtual addressing that it changes its address, at least the reference to the address, and that's because what happens is we create something called a page table. So, and let's bring in our secondary storage as well if you want to run larger programs. Right? So what ends up happening is, let's say you have only 4 gigs of RAM, right, and you have a 16 gig program. What ends up happening is if the 16 gig program lies somewhere in secondary storage, it will only load the things that it needs at the time, right? So if, let's say, for instance, I'm using Photoshop right now, and I have a bunch of brushes that I'm not using, right? So maybe I have like a collection of brushes here, or like a collection of fonts that make up maybe like 5 gigs of my storage space in Photoshop, right? But if I'm not using all of those features, it's only going to load in the features that I need. And what happens is it goes in and it puts it into a page table. So this is just like Photoshop features in use, right? And then that gets mapped somewhere in memory that's loaded in, right? So maybe this takes up 2 gigabytes of RAM, right? So I have 2 gigabytes allocated for that. And this is the physical memory. So this is the actual stuff in RAM, physical or RAM. And what happens is these programs go into the page table to find where it's linked to in memory. So while these are fake addresses, right, they're basically just mapped to the physical location itself. Okay. But that's how you're able to run multiple programs that might otherwise saturate the entirety of your physical memory and still be able to run them simultaneously. Because we kind of do this thing, but the overhead comes from all this backtracking of creating a page for it, and then searching the page in memory, passing it back into the virtual memory that runs the program. And if you run out of page table space, you'll learn more about this in OS, but basically they follow some different algorithms. The most frequently used one is the least frequent
used model. So the longer a page hasn't been invoked or searched up, the more likely it is to be removed in place of something that needs the new page memory. And that kind of also ties in with how cache works too. Some algorithms in cache basically revolve around the least frequently used memory allocations get wiped first because the space is just limited. Okay, so hopefully that gives you a little bit of insight on some of these little things that kind of go with our architecture. So you'll get quite a bit of these architectural questions that kind of tie into the von Neumann architecture on your test. So just make sure you kind of get a broad understanding of what these concepts are and how they benefit our systems. Okay. But that is all the new material that you'll have to know for the test. And we can kind of go over the quiz and the test review stuff. So is there any questions on any of the concepts that we kind of touched up on today? Those concepts I don't believe are on the textbook, so but you won't be tested extensively on those since they're just kind of like introductory concepts that you'll see in later classes. Okay, so let's go ahead and take a look at your quiz. Okay, so we can run through this really quickly. What is the first step of the JAL instruction? Remember the JAL instruction, we need to do two things. The first one is not push the program counter, but to copy it into the RA register, right? Remember, one of the reasons why RISC is faster than CISC is because of this step, where instead of pushing our next instruction register, we just copy it into another register. Okay. Question 2. So this is a follow-up question, which is the reason why, or which of the following scenarios does the RISC architecture perform faster than the CISC architecture regarding function calls within functions? Now, we covered this yesterday, but just a refresher. So remember that we have our JL label, and this copies PC into RA versus the call label, where it pushes RIP onto the register. All right. They'll both jump to the function, obviously, but the difference between this step and this step makes a big difference when we're doing our function. So let's make this F1. So in F1, right, there can be multiple cases that happen. So let's say in F1, there are no function calls. No function calls. Okay. Well, here in the first case, we can look at both our stacks, right? So stack here and stack here. So this is the RISC and this is the CISC, right? So the first time this happens, PC into RA is a register to registered instruction. So there's no use of memory or no need to access memory, therefore no bus contention. So this is a case where case 1 is no bus contention, which equals faster. Okay. Case 2, so in this case, we push RIP onto the stack. Case 2, we have one function call. So let's say we say JAL F2 or call f2, right? So function call within a function call. So remember, when we do that, we have to push RA and pop RA, right? Of course, this isn't push and pop are not implemented for you. I'm just using the comments to show you that that's what you needed to do. But we'll have RA on the stack, and we'll have RIP on the stack. And then we have to access the stack one more time. But if we're just solely talking about this, RIP gets pushed on a stack and then popped back and then pushed, and then popped back one more time, right? So RIP gets on the stack. So technically, it's a little bit faster, but it's negligible. So we usually say there's no change. But it's more obvious when we go into F1 having multiple function calls, right? And then call equivalent. Okay, but we only had to push RA once. Push and pop RA once, whereas we had to push RIP multiple times, right? Depending on how many functions. So this is the first RIP in the main. This is RIP in the first function, RIP in the second function, and so on and so forth. So by using invoking the stack multiple times, we're essentially invoking a lot of bus contention. So whereas the register model, or copying to a register model in the RISC architecture, is faster because we only had to push once per multiple function calls. Of course, it's different if F2 had multiple function call or single function calls in it, and F3, and so on and so forth. But in general, we can say that multiple function calls should be faster. Okay, so question 2, multiple function calls and no function calls. Question 3, what is the step to push the operand onto the stack in RISC? So on the test, I'll specifically tell you whether it's RISC or CISC. But a general rule is that all the questions regarding CISC will be on the top, and then all the questions about RISC will usually be on the bottom. So that way it's a lot harder. Can you explain why it's faster when no function call? So with no function call, right? We're just doing we're just copying PC into RA once, which is a register to register, which means we do not use the bus, right? So if we look at the von Neumann architecture, so register to register is inside the chip, right? So copying PC to another register does not utilize the bus and is therefore faster. While when we do a function call in the CISC architecture, we have to push RIP onto the stack. You remember that the call instruction does this operation for us. So because we have to push RIP, so if RIP is here, right, we have to push the contents onto the stack in memory, right? And that will that'll take longer than just copying it to register. So first step to push an operand to the stack. Remember, when we push, we have to first allocate space. And in a 32-bit architecture, we allocate 4 bytes. Okay, so remember, we go down on the memory since we're working from higher memory to low. So here we subtract the stack pointer by 4, and that is how we allocate the space for it. You're confused? I don't know how to explain it any further than that. So on a function call, we say JAL function 1, right? Or call function 1 in Sysc. It's okay, we have time to go over it. It's not a big deal. Okay, so JL and call, right? Remember that JL is the equivalent of push or copy $PC to $RA. And the equivalent of call is push RIP onto the stack, right? So we know that the stack, so this operation uses the stack, right? Or in other words, we need to go into memory, right? And to go to memory, that implies we have to go through bus, right? Remember what bus contention is, that whenever you utilize the bus, if the bus isn't available, so if another process is currently hogging the bus, let's say you're downloading the Qt Spim and you have to load into memory, then the bus is going to be occupying by downloading all the stuff, right? So it goes from RAM to secondary storage. And so you're not able to run this push RIP command or instruction while the bus is being occupied, right? But here, there's no bus contention because we're copying a register to register. So this is register to register. So we know that in CPU, all the registers are here, right? So this is PC, and maybe this is RA, right? So doing an operation that involves two registers together is fast. Not only because of its locality, but because we don't have to access the bus to do it. We don't need to wait. Someone says, register operations are faster. By not using the stack, it's inherently fast. Yeah, so by not using memory, the operations are inherently faster. Yes, so the main function is calling F1, and that is the only function call. And inside F1, we're saying in this example, or in these scenarios, the first scenario is that F1 has no function calls. The second scenario is that F1 has just one function call. And the third one is that it has multiple function calls. Okay, so hopefully that makes sense now. So all good. As long as it makes sense. Okay. Question 3, which is the first step to push the operand on a stack? We allocate 4 bytes of memory because in RISC architecture, we are dealing with 32 bits, which is 4 bytes. So that is the appropriate answer for that. You might see the same question, except I won't be giving it as a multiple choice, maybe. So a lot of these might not be multiple choice questions. I did it so that the grading would be faster and you'll get your results back. So at least you can study for it. Question 4, define recursion. So remember, we talked a little bit about recursion at the end of class yesterday. And it is simply just solving and or defining a problem as a smaller version of itself. So remember the factorial problem, we had factorial of 5. We can break that down into 5 times factorial of 4, right? So you'll still have to do the factorial problem, but now it's a smaller version of that factorial. Okay. Question 5 says, the 2 things we benefit from using cache. So we reduce bus contention, right? So much like register to register, cache is very close to registers because they're in the same block in the von Neumann architecture. They're in the CPU chip. So no need to access the bus, which does reduce bus contention. and we reduce memory latency because we no longer need to always ask our primary storage to give us our variables if they're already in cache. So what the system will do is they'll first look into the first level cache. If the variable's not there, or if the memory's not there, it goes to the next layer of cache, so level 2, and then if you have level 3, goes on and on. Why do processes utilize pipelining? So remember, with pipelining, we are essentially loading up different stages of our process so that we can do them as soon as they're available. It's not the same as parallel processing when you're doing the same operations in parallel. So the difference here is, let's go back to pipelining really quickly. So here you can see that the pipeline looks like this, but if we were to visualize this as parallel processing, so parallel processing would be the same as, let's say we have 5 threads and they all run the same thing, right? So this is what it would mean to run it in parallel. These are all the same, right? So maybe in this case, we ended up, let's say like each operation takes 1 millisecond, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9. This would take 9 milliseconds, right? But this would just take the 5 milliseconds if it was ran in parallel. Okay, so it is not the same as parallel processing, despite what it looks like. To utilize more CPU time, that is not necessarily correct. To wash, dry, fold its clothes, that is also not correct. But it is to increase efficiency and performance. I guess in parentheses you can say it for your processes, but that is why we utilize process or pipelining. Okay, last question. Why do processes utilize virtual memory? So this is a multiple answer one. So to stress the programmer with page faults, that is not true, but you kind of now know why you have page faults, right? If it's unable to find a page that it's expecting to point to a memory location, that is why you'll get your page faults. To save computation time, that's not necessarily true. To be able to load larger programs than RAM can hold, that is a good benefit of having virtual memory. You can now load Minecraft into your Raspberry Pis. To be able to run multiple programs, that is also true. Because if multiple programs occupy too much space, as long as your virtual memory is asking for the important parts that are necessary to run the program, you can run them simultaneously. Okay, so that should be all the quiz answers for today. So any questions about the quiz? Just make sure you do this quiz before the test starts. So I think I set it for 1 o'clock tomorrow. So you'll get almost the full 24 hours to do it. Should not take you that long, especially since all the answers are given out. But it's mainly to just kind of refresh your memory on all the topics we covered this week, and also utilize it to study for your exam. Okay, let's go ahead and look at the pages. So here is your final exam topics. So essentially, we get to read the syllabus again. No, but I'll emphasize these are the topics that are going to be more emphasized. So the first part of the test is going to be CISC specific. So everything we've kind of touched up on in x86. So make sure you know your registers and the functionality of them. So things like realize that the multiply instruction will store your answer into RDX, RAX, or the DA registers or the AL registers if you're using byte multiplication. We need to set CDQ or C convert whatever data type into the appropriate one for division, as well as realizing that the remainder is in the D register. So the quotient is in the A register. We should know the different save registers according to the standard calling convention. So like RBX, R12, and so on. Argument registers, so RDI, RSI, RDX, RCX, and so on. Stack pointer, so RSP, your base pointer, RBP, and your things like your RRP, points to next instruction. Just the general stuff that you've been handling with, maybe R flags, stuff like that. We went ahead and talked about the stack. So we push and pop instructions. We learned that it was following the last in, first out kind of structure. Then we went ahead and talked about the standard calling convention for functions. So this is probably a big part of the part for CISC at least. So just maybe write a function, or much like the last exam where you had a two-parter, you have to do the function call. So doing the arguments, making sure you update your stack pointer, and then write the actual function. So know how to access your arguments either through the registers or on the stack. You might have a question on stack dynamic locals. But be able to write a small program or function that follows the standard calling convention. Of course, you'll need to know some basic instructions like your arithmetic instructions, so add, subtract, multiply, divide. Remember your movement instructions, maybe your comparison and jumps, all that good stuff. It might utilize your float instructions, so make sure you kind of know that. I might try something different where I write the code and then you give me the result. So we'll see about that. RISC. So this is all the stuff we've been covering this entire week. RISC is basically need to know the differences or the similarities and differences between the two different architectures. So know the differences in the registers as well, because there's a few little nuances like the PC is for the program count, the program counter, which is the same as RIP. Just know those. I prefer on the test if you use the register names and not the register numbers. So use things like T0, T1, and not, I don't have the MIPS book open, but let's go ahead and open that. So you'll notice registers, CPU. So yeah, use T0 to T9, but don't use things like $8, $15. That just helps with readability. So know why certain instructions or architecture choices improve performance over CISC. So some examples we covered already was, say, when you're doing the calling convention for functions, we realized that saving the next instruction register into another register is a lot more efficient than, say, utilizing it or popping it or pushing it and popping it onto the stack. What is the ratio of CISC and RISC questions? I don't know. I would say I want to give you more RISC questions, but a lot of the RISC questions also involve CISC, like the comparing things like this, copying why this instruction in particular has performance increases as opposed to the other architecture. So a little hard to say. But if you're familiar with both architectures, then you should be fine. write a small function or program in MIPS in accordance with the SCC. So you got to know what your function calls are. You need to know what your argument registers are, where your return value comes from or stored in, all that stuff. So, but that should be no problem considering that you are doing your 2 assignments, and those should prepare you pretty well for those. Same thing. I might give you some code in Float and then ask you what it is. So just be able to read the code. Stack memory addressing. Yeah, so know how to do push and pop in RISC because it is not a built-in instruction. And then here is the MISC architecture. Haha, just kidding. It is the miscellaneous kind of topics we kind of covered that kind of fit into both categories, but they're more like concepts, not actual coding. So remember when we talked about interrupt handling, we talked about how the syscall is an interrupt, and then we went through the 5-step process of interrupt handling. We went through a lot of von Neumann architecture, so this is important because now we understand where our bottlenecks occur. So bus contention, how memory works, maybe some cache question or two. These aren't going to be very specific. They're more going to be like why might have some performance increase utilizing cache or something. Recursion, same thing. So recursion, pipeline, and virtual memory, those are going to be very light questions. They're not going to be too in depth because we didn't really go into extreme detail on them. But it's still just good to know as a broad concept. Input buffering. So we still need to remember why we need input buffering. Of course, a lot of these are topics on performance enhancements. Stack buffer overflow, that's another one. We talked about toolchain, so this might come back and haunt you. And parallel processing and race condition, another broad topic we touched up on that also has to do with performance increases. So all these miscellaneous topics usually have something to do with performance and bottlenecks. Maybe interrupt handling is a little bit different, but you should basically more or less know how your program works with all these topics. Will we have to write code with float instructions and RISC? No, you will not have to write code for RISC, but you might need to read code with float instructions. I haven't decided on whether or not I'll include those types of questions. I'll just have to basically, once I make the question bank, I usually add in questions or take out questions depending on what I feel the topics we need to kind of make sure you guys know. So it's going to be roughly cumulative. We're going to have some new questions on RISC. So make sure you study your quizzes and make sure you kind of understand how to program in the RISC architecture and the differences in the two architectures. Those are the big ones. And then just don't unlearn everything in the last 4 weeks about CISC, and you should be fine. Can you show how to run code in Qt-Spim? Yeah, sure. No problem. And am I teaching any courses during fall semester? No, I'm actually not teaching any courses. I will be TAing for Dr. Togva's database class, though. There will not be any read from files with MIPS, although I think the instructions are in the MIPS textbook. So let's see. There should be a documentation on that. Good programs, procedures, system services. So there might be some on reading file. Yeah, so open file, reading file. If you really wanted to code in MIPS, I'm not going to put this on the test. But if you wanted to read files and write to files, I'm sure you can hack the code with that. Shouldn't be too different from our x86 architecture. Let's go ahead and pull up QtSpim. So it's not overly difficult. So when I launch QtSpim, I'll get a console. You might not have this. If you don't, just go ahead and hit Window Console. So your blank QtSpim should look like this. There should be no code in the middle of kernel and this user text segment. And all of this is basically the code that the simulator uses. If I wanted to load a program, I usually use this one, which is reinitialize and load. So that just makes it so that it wipes anything that was in the previous code that's being used. Let's go ahead and open. Which one is a code written in QtSpim or written in MIPS? Let's see. So, okay, so here, maybe I'll try to open this in Visual Studio Code first. So, let's do this in here. See, yeah, so this is the simple Hello World program that every programmer needs to know how to do. So, all I have to do is open it up here. So I hit open, and then you'll see that it loads the code. So line 9 is where the code starts, all the way to 14. So you'll notice that the code is loaded in here. All I did was hit this and then open the file from there. And then we can run the code by just hitting this play button. And you'll see on the console, it prints hello world, tells me what line is being executed, which is the sys exit right here. But that is it for that. If you wanted to look at the data, you can see. You'll see right here, hello world is inside one of my datas. And if you wanted to look at the stack, I guess you can look at it here. Of course. Okay, so let's see. When you do QtSpim, can you purposely make an error and go over debugging a bit? Maybe. I don't know what kind of error you want me to go over. Someone said I did a lot of debugging by setting breakpoint and running, then hitting single step and using F10 to go step by step. Okay. How time error? Let's see. If there's any useful settings. Length file. I think there's any interesting things we need to do. Okay, so the relationship between what QtSpim throws and how to find that in our line of code. Okay, so maybe we can edit hello world a little bit. So let's go ahead and maybe do something illegal. So let's define the variable var1 as, let's just not use the colon and just say word and then 3. And then let's say this is illegal, but S0, and var1. Okay, so I have two legal things going on. And then let's okay, so when I run it, it gives me this error. It says spin parser is a syntax error on line 3. So where it says .world or word 3. So it tells you what line it is. So
we pull it here, you'll notice that it does match the same line in my text editor, and that is because we don't have the colon. So let's go ahead and save that, and then we should have one more error. So I'll open the file again, and then here I'll say in line 9, syntax error here. Obviously, I can't do I have to do a register here, so I have to do something like S1, and then maybe we'll do load word S1, R1, li 0. Let's do 2. Let's change it up. So, and then if I were to run this, it shouldn't have any program issues. So here, it's fine. So if I run it, I should see that my S1 is 5, which contains 2 plus 5, which is correct. And then that contains that. Yes, you could set breakpoints as well. So just right-click breakpoint and then run it a step at a time. So that way you can check your registers as you run it. Okay. If you have any more specific debugging questions, but I wasn't sure what you were looking for specifically, if anything. Okay, so is there any questions on any of the topics that we have? Anything for your tests or quizzes, homeworks? Mine is just to end a loop correctly. I'm trying a counter, but it's not working. I'm not sure. Do you have a logic error, or are you just not updating your counter correctly? So for the students that don't have any questions on the topics of the homeworks, you guys are free to go. So just make sure you take your test at the appropriate class time. I'll send an announcement saying that the test is uploaded, and then you guys can check whether or not the information on there is correct. So it's the starting ending times. But that's about it. You guys are almost done with 218. Hopefully it wasn't as horrendous as some of the horror stories. So yeah. So this was officially my first teaching class, so you guys get to be my guinea pigs. Haha. It's not bad at all. That's good to hear. You're a good teacher. Oh, thank you. Thank you for making this class bearable. But yeah, yeah. So 218 is not too bad, but just make sure you finish your quizzes and your assignments at the appropriate times, and then the final shouldn't be too bad since you've already taken test 2 last week, so a lot of the stuff is still fresh, and then you just have to do a little bit of nuanced stuff with the risk, and that's it. All right, so I'll stick around for a little bit in case you have any questions, but if you don't, just take the rest of the day to finish your homework, finish your quizzes, and then maybe do a little bit of studying on the exam. You guys generally do pretty well. Like the average is about
89%, 87-ish. So I don't think if well, the test is going to be more or less the same amount of difficulty, just with maybe introduced topics. So you should be fine. All right. Yeah. So I'll stick around and answer some questions, or if you want to just chill, it's fine too. Next session isn't for another like almost half hour, so maybe you'll just play some music, chill until then. Streamer's tears as a memento. Yeah. Did I ever update Streamer's tears? No, I haven't. Right. Oh no, I need to make sure I don't lower the streamer points anytime for you guys. And make sure that I can't I don't give out freebies. I guess I can upload the notes now, so I have some time. Today is the 8th.